So we talked in our last lecture about deviations, and now we're going to begin to talk about the standard deviation, which is a concept that you'll work with for the entire rest of the semester. So let's begin by reviewing how to calculate the mean and the deviations that we had in previous lectures. So we know that the formula for calculating the mean equals the sum of all the scores divided by n, the number of scores. So let's calculate the mean. If we sum up all of these scores, we can see that the sum equals 32 divided by n, and we can see that there are 8 children, so 32 divided by 8 equals 4. So we know that the mean equals 4, and we know that the deviations formula is x minus m, and so our first child had 7 hops, minus the mean of 4 equals 3. Child 2 had 1 hop, minus 4 equals negative 3. 6 minus 4 equals 2. 4 minus 4 equals 0. 5 minus 4 equals 1. 4 minus 4 equals 0. 2 minus 4 equals negative 2. And 3 minus 4 equals negative 1. These are the deviations that we'll be using when we calculate our standard deviation. So what do we mean by standard deviation? And to answer this question, let's consider this example of homemade flutes in remote regions. So this is a professor that I worked with back in North Dakota whose doctoral dissertation involved going to very, very remote regions and keeping track of what intervals there were between the notes in the common music of that region. He was a music professor. And if you'll notice these old flutes, you can see that the holes are differently spaced. That means that the pitches that comes out of these flutes are going to differ, or the distance between the tones are going to be different. When this guy, for example, from one region brought his flute and went to another region and wanted to make music with people from the other region, it didn't sound that great. That's because the musicians had no common language or standard for pitches, so their pitches wouldn't blend well. Since it was hard for them to play music together, they created a common standard. And much of the music in our world today relies on these common standards, like the thickness of the guitar strings or the violin strings, or the pitches that a person can make on some sort of a wind instrument or a piano. So when we say standard, we're talking about, and the definition reads, an accepted or approved instance or example of a quantity or quality against which others are judged or measured or compared. And so you can see that we use standards all over the place. We use a standard measure of inch. That's the standard agreed upon unit of dimension in the United States. Here we use minutes, second, hours throughout the world. Quarts and ounces in the USA, this is the standard that we use for measuring liquid. And of course, pound is our standard of weight in the USA. It would be hard to communicate if we hadn't agreed on some standards. Likewise, imagine buying fruits or vegetables without a standard. Well, I'll sell you a bagful for $1.99. Well, how much is a bagful? Bagful is not a standardized measurement, so the weights on the top of the scale image, we don't know if they're standard for that area. They're weighing these weights, but how do we know? So we agree on it. It represents what's normal. A standard deviation is the standardized measure of spread in a particular distribution. So it tells us in this distribution, what is the typical distance of each score from the mean? So in other words, it's like the distance a typical score in this difference deviates from the mean. If we use that word deviation, standard deviation. Standard deviation measures the spread of the distribution. If the distribution is narrow, then the standard deviation will be a small number. In this case, in the top graph that says small standard deviation, these colored lines represent the deviation. And you can see that it's very small. The spread goes all the way from 70 to 90, but this is a standard of how far the scores deviate from the mean, as is this. And it's about maybe 1.5 for the standard deviation. In this large standard deviation down here, you can see kind of the same range. It's ranging from 65 to 95, but here you can see the standard deviation is much larger. The scores are spread farther. In this case, the standard deviation is about 4, and it's marked by these lines that are coming down here. So these lines represent the distance of the standard deviation. We can say that this one is about 4. Well, you can see it's 5 actually. This one is about 5. The numbers aren't quite lined up. So we can see here that wide distributions have larger standard deviations than smaller distributions. So back to our houses, we can see here that we have a small standard deviation. The standard deviations fall something like this. And we can see that they're really not very far from the dotted line in the center representing the mean. So this distance is the standard deviation. Figure B depicts high variability, and you can see it looks something like this. This is about where the standard deviations would be, and you can see that they're quite a bit farther from the mean. So a little bit more. We already know that to calculate a deviation, we take each score minus the mean. So if Tara's grade was 88 and the mean was 78, her deviation score equals 88 minus 78 equals 10. And we can see similar examples. We've done quite a few of these so far. So first of all, standard deviation can be conceptualized as sort of like the average of all of the deviations. We abbreviate standard deviations as SD in situations where we know every data point. But because the actual average of all the deviations would be approximately 0, we add a little bit more to the formula. So I'll give you the whole formula and then we'll break it out. So the entire formula is SD equals the sum of all the deviations squared divided by n, and we take the square root of all that. Now, this part of the formula, right here, the sum of all the squared deviations, we're going to call the sum of squared deviations, or SS for sum of squares. When we divide it by n, we're going to call it the variance. And when we take the square root, that's when we get the standard deviation. And we're going to break this formula out in our subsequent slides. So let's try an example. A particular basketball player kept track of how many points he scored in each game during the season. The points he earned by shooting baskets are below. These are the scores for each of his games. What we're asked to do is find the mean, median, and mode for his scores, and then to find his standard deviation. So let's go ahead and solve what we can here and then continue on the next slide. So first of all, we can just look for the most common number occurring to get the mode. And so we can see the only number I see that's duplicated is this 6. And so we know that the mode equals 6. To get the median, we have to rank these numbers. in order from lowest to highest. So 0, 2, 3, 4, 5, 6, 6, 7, 8, 9. And if we go 4 this way, 4 this way, this is what's left in the middle. And if I take the middle of that, I know the median is 5.5. To calculate the mean, I need to sum up all the scores and divide by the number of scores. And the number of scores in this case is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's write that information down. N equals 10. M equals the sum of all the scores divided by N. And so the sum of all these scores are 9 plus 8 is 17, 19 plus 9 is 28, 35, 40, 50. Is 50 divided by 10 equals 5. So 5 is what we're going to take away from every score in order to get the deviation. Go ahead and calculate this. Here are the scores up above, and I've written them down here. We have to calculate the deviations, x minus m, so I'll write this here. Deviations and x minus m. So these scores are x, 0 minus 5 equals negative 5. 3 minus 5 equals 2. 6 minus 5 equals 1. 8 minus 5 equals 3. 2 minus 5 equals negative 3. 9 minus 5 equals 4. 7 minus 5 equals 2. 6 minus 5 equals 1. 4 minus 5 equals negative 1. And 5 minus 5 equals 0. So we know that our formula for standard deviation in total looks like this. Standard deviation is the sum of all the squared deviations divided by n, and we take the square root of that. So the first thing we're going to figure out is the sum of squares, which is this part of our formula. So the sum of squares equals the sum of all the squared deviations. And so let's figure out the squared deviations. Deviations squared. Negative 5 squared equals 25. 2 squared equals 4. 1 squared equals 1. 3 squared equals 9. Negative 3 squared is 9. 4 squared, 16. 2 squared is 4. 1 squared is 1. Negative 1 squared is 1. 0 squared is 0. So if we add these together, we have 22 plus 18 is 40, 45, 50, 70. So our sum of squares is 70. And I did that again by adding all these together. The next thing we figure out is our variance, which in terms of our formula is equal to all of this before we take the square root. So in other words, the variance, and we'll use this color now, the variance equals the sum of squares divided by n. In this case, our sum of squares is 70, divided by n is 10, equals 7. And so our variance is 7. To get to the last step, we simply take the square root of the variance. So our standard deviation equals the square root of the variance. And the square root of 7 is what we're looking for. And the square root of 7 is approximately 2.6457. And with that said, you might be wondering, how many decimal points do you need to use? And so let's give a little rule of thumb for decimal points. When calculating, use at least 4 decimal places. So 1, 2, 3, 4, that's what we'd use. If we're writing up a result, no more calculations, then we use 2 decimal places. So if we were writing this in a result, we were writing standard deviation equals 2.6, and we would round this 5 up 1, so we would write 2.65. So we'll be going through more examples in later slides. This is just the conceptual framework.